Today we are going to discuss about types of magnetic circuits. The magnetic circuit can be categorized based upon the connection scheme as series magnetic circuit or parallel magnetic circuit. In case of series magnetic circuit, we are having a different size of magnetic paths. Let's consider there is a one magnetic path having a length of L1, whereas the another magnetic path having a length of L2, similarly L3, L4 and L5. These magnetic paths may be of different cross-sectional area. Let's consider for first path it is area is A1, in second path area is A2, in third path area is 3, A3 and A4 and similarly A5. By the definition, we know S is equal to L upon mu A. Here L is the length of the conductor, A is the cross-sectional area of the magnetic path, whereas mu is the permeability of the magnetic path. And if it is for one type of material, then it will be L1, A1 and S1. Similarly, if it is for second type of material, then S2 will be equals to L2 upon mu A2. Now, similarly in this particular circuit, the magnetic circuit in which flux through different cross-sectional or material in a single path remains same is known as series or composite magnetic circuits. This is shown in this figure. Here there are five different magnetic materials, and corresponding to these five magnetic materials there are five different reluctances S1, S2, S3, S4 and so on. Now, by the definition, we know magnetomotive force, that is MMF, is given by N into I, which is equals to S phi, where S is the reluctance and phi is the flux. From this equation, we can putting the value of S over here. In a series circuit, the total reluctance of the path is S1 plus S2 plus S3 plus S4 plus S5. Therefore, putting the value of S1, S2, S3, S4 and S5. It is phi into may S1, and then it will be that it can be written as H1 into may L1. Similarly, phi into may S2, it can be written as H2 L2. Then phi into may S3, it can be written as S3 L3 and so on, corresponding to fifth, fourth and fifth length of iron piece or magnetic path. Now, considering the parallel magnetic circuit, in case of parallel magnetic circuit, the total flux developed by the circuit is energized from electrical supply. Let it supply is connected over here. Then current is flowing in this circuit is I. This causes the flux develop in this path. This flux is having two different paths following phi 1 and phi 2, such that phi is equal to phi 1 plus phi 2. Now, representing this circuit equivalent to a electrical network, this is the reluctance of this path where it is total flux is developed, whereas reluctance of the path where flux phi 1 is developed and reluctance of the path where flux phi 2 is developed. The total flux developed in this path it is phi, whereas this flux is phi 1 where and this flux is phi 2. Similar to an electrical circuit, when we are going to apply EMF or voltage at this point, the current flowing in this circuit is I, whereas the current in these two paths will be I1 and I2, and I will be equals to I1 plus I2. Similarly, in a magnetic circuit, the total flux is phi, whereas total flux is divided in two components, phi 1 and phi 2. Therefore, phi is equal to phi 1 plus phi 2, and hence this is a parallel combination of the two magnetic paths. Now, in this magnetic path, the total flux or total MMF developed will be equals to the MMF in these two paths. This is the total MMF. The MMF in this path is phi into S. The MMF in this path is phi 1 S1. The MMF of this path is phi 2 S2. By the KVL, the total flux developed total mmf of this across this reluctance, it is phi s, and total mmf developed across this reluctance is phi 1 s1. Therefore total mmf in this circuit is phi s plus phi 1 s1. Similarly, if we are considering this path, then it will becomes equal to phi into my s plus phi 2 s2, and which is defined over here. And hence we can say electrical series circuit and electrical parallel circuit is just equivalent to magnetic series circuit and magnetic parallel circuit. Now, in a magnetic circuit, there is air gap, and this air gap is desirable. Why it is desirable? Because when this supply is connected over here, the current is flowing in the circuit, causes some flux develop in this path. Then the this magnetic core is having a property that when the current is going to be increased, a stage will come when there will be no more increase in flux, and this is known as saturation. To avoid this saturation, we are creating a small air gap. Generally, it is of 1 mm or even less than that. That with this air gap, the saturation, there will be no saturation, and the relationship between I and phi will follow a straight line, and this magnetic core will never be saturated. Now, therefore, in this in this case, we can consider there are two paths. One, it is due to the iron, and another is due to the air gap. And hence, there will be two different reluctance. One reluctance due to the iron path, that is Si, let it is, and another reluctance is due to the air gap, let it is Sag. And in case of total ampere turns, that is At, or in other words, it can be written as Ni, that is mmf, will be equals to B upon mu into my Li, and due to the air gap, it will be B upon mu into my Lg. Lg is the length of air gap, where Li is the length of iron path. The iron path is the rest of the part other than this part. Now, taking B upon mu naught common, then L1 Li upon mu Ri plus Lg upon mu Rg, because in case of air gap, relative permeability is always equals to 1, and the absolute permeability, that is given as 4 pi to 10 to power minus 7 Henry per meter, it is common for air gap as well as the iron path. In this case, there is only one iron path. If there were more than one iron path, then accordingly we have taken over here S1 plus S2 and so on. Now, the loss in a magnetic circuit due to AC excitation. AC excitation develop magnetic field which is pulsating. Pulsating here means, then in case of AC supply, there is a plus minus of the polarity for voltage. If it is a voltage and if it is a current, there will be plus and minus, and it causes the field when at one instant, if it is north and it is south, at the another instant it will be reversed, it will become south and it will become north, and hence this is pulsating in nature and causes two type of loss in the system. And the first loss is considered as hysteresis loss, and second is known as eddy current loss. Hysteresis loss occur due to the reversal of magnetism, whereas eddy current losses occurs due to the eddy current circulated within the core itself, and hence these losses are counted as I square IE square RC, where RC is the resistance of the core of the magnetic circuit. Now, considering these two components, here first we consider eddy current. In case of eddy current, there an empirical relationship have been derived when we consider the, the AC, this magnetic core or magnetic circuit is energized with AC supply having a frequency of F, and the thickness of the core is, let it is T, the applied voltage is V, and the flux developed having a maximum flux density and B max. When this repeatedly this experiment have been performed 1 2 3 and so many times, and finally we concluded that there is a relationship between these parameters considering some constant, and this constant is known as eddy current constant. Considering that with the magnitude of this constant, the variation of eddy current loss is found to vary with square of the maximum flux density, with square of the supply frequency, square of the thickness of the core, and hence the thickness of the core, if it is single or solid structure, then the thickness will be more, and hence this thickness, this instead of using the single core or solid structure of the core, we are dividing this core into number of layers, and these are known as laminations. And hence we used to say the core of the transformer is a laminated core. Now, with this laminated core, the total loss developed in due to eddy current is given by Ke B max power to F square T square V. And in other words, we can say eddy current loss is directly proportional to the supply frequency, thickness of the core, and applied voltage. Higher the voltage, higher will be the eddy current loss. Higher the supply frequency, higher will be the eddy current loss. Now, considering magnetic and electrical circuit together, there are some similarities and dissimilarity between the electrical and magnetic circuit. Considering the similarity first, in electrical circuit, we are having EMF as a driving force, whereas in magnetic circuit, there is a MMF which is having 80 ampere turns or simply Ni. Now, in electrical circuit, there is a response is considered. When response is concerned, the response is current, which is given by E upon R, whereas in magnetic circuit, response is flux, which is AT upon S, ampere turns upon reluctance. In electrical circuit can be represented as series and parallel combination of these resistances. Similarly, a magnetic circuit can also be represented as series and parallel combination of the different reluctance path. The reluctance of this is S, the reluctance of this S1, the reluctance of this path is S2. And hence, these two circuits are just equivalent to each other. Here the source is EMF or voltage, here the source is MMF, that is given by N into I. Now, another is field intensity. In electrical system, the field intensity is given by volt per meter, whereas in magnetic circuit, the field intensity is given by ampere turns per meter, and ampere turns depends upon the number of turns and the current in the circuit. In electrical circuit, the voltage the voltage across a resistance is considered as voltage drop, whereas in magnetic circuit the mmf drop across the reluctance S is considered as mmf drop. If it is S1, then it will be voltage drop across S1. If it is S2, this is mm drop across S2. In electrical circuit, we are having current density, which is given by current per unit area, that is A upon I upon A, whereas in magnetic circuit we are having flux density, that is flux per unit area, Weber per meter square. But considering the similar dissimilarities between magnetic and electrical circuit, here we can say in electrical circuit current does actually flow in the circuit, whereas in magnetic circuit flux doesn't flow. It is the static quantity which once developed will remain same throughout the operation. In electrical circuit, current can flow in a complete path, whereas in magnetic circuit, flux can pass through even air gap. Air gap in electrical circuit create an open circuit, means if their circuit is open, then there will be no current and current reduced to zero. Whereas in case of magnetic circuit, air gap is desirable to avoid the magnetic saturation. Otherwise, there will be no more increase in flux with the increase in current. In case of electrical circuit, when current reduces to zero, the source reduces to zero after removing the source from the circuit, whereas this is not the case in magnetic circuit. When we remove the source or magnetizing source of the circuit, then there will be some residual magnetism, and this residual magnetism causes some magnet within the core of the magnetic material. The another dissimilarity is the continuous loss in electrical system. When there is a current flowing in the circuit, always there is I square R loss, and this is multiplied by T, then it is known as heat. As long as there is a current in the circuit flowing, there will be heat loss. Whereas in case of magnetic circuit, as long as there is a flux, it doesn't mean that it is going to create any kind of loss in magnetic circuit, because flux is not actually flowing, whereas current is actually flowing in the circuit causing dynamic operation, whereas flux is a static quantity.